In our rates question number 4, it's from the 2016 exam, and this is a classic rate in, rate out type of a question. I'm given water being pumped in at a rate given by W of T, and I'm also given water is being removed at a rate that is given in our table above. In part A, we're asked to estimate R prime of 2, and what I have in my table are R values. So what I'm going to do is use an average rate of change to approximate this instantaneous rate of change. We've done many problems like this one. So this is just finding where 2 falls in our table, and it's right in between the 1 and the 3. So this is the part of the table I'm interested in. And I just do my y2 minus y1 over x2 minus x1. Make sure you show the difference and the quotient. It's called a difference quotient. Simplifying is optional. If you simplify, you get negative 120. But it also indicates that you must give units of measure. So the 950 and the 1190, their units are liters per hour. So I just put liters per hour in the numerator. And the 3 and the 1, their units are hours. So I just put hours in the denominator. It would be fine to leave the unit in this format, but if you want to change it to a more of a typical acceleration unit, you could write it as liters per hour squared. Point-wise, this difference quotient is going to earn you a point, and correct units is going to earn you a second point. Part B is asking for a left Riemann sum with 4 subintervals indicated by the data in the table. So I look up at my table and I can see my first subinterval is 1 unit long, and then I multiply times the height on the left side. So my first rectangle is a 1 by 1340. My second one is 2 units wide times the height on the left is the 1190, so 2 times 1190, plus the third one is a 3 times 950, and my fourth is 2 by 740. So it's just the difference in the interval times the height that's given on the left, because this is a left Riemann sum. Simplifying that, calling that 8050 is optional. You get a point for a correct left Riemann sum here, and a point for that correct answer. If you don't give this answer, then what I have boxed is going to earn you both of these points. I'm also asked if this is an over or an underestimation. And I know when I do a left Riemann sum, what determines that is the increasing decreasing nature of the graph. So I go back to the stem of the problem, and it tells me that my function r is decreasing. And if I draw a little decreasing graph here, and I do some left approximating rectangles, and I know they're left because the left corner is sitting on the graph, I can see that this is going to give me an overage because I'm capturing areas here that aren't really under the curve. So therefore, I know that because r is decreasing, this is an overestimation. To say over with, and the reason being r is decreasing is going to earn you a point. Make sure when you give this reason that you say which function it is that you're talking about. So don't say it is decreasing. Name it by name, so r is decreasing. Part C wants me to estimate the total amount of water in the tank to the nearest liter at the end of 8 hours. There's 3 things to consider. The amount of water that is there initially, which is the 50,000. I need to add the amount that is coming into the tank, so I'm going to integrate that rate, WT. And then I need to subtract out the amount of water that's leaving, which is actually just my answer from part B. And when you put all that together, rounding it to the nearest liter, you get 49,786. Point-wise, if you have this correct integral, just this part right here, that earns a point, and everything else to arrive at that correct answer earns you a second point in part C. And then in part D, it wants to know if there is a time at which the water being pumped into the tank is the same as the water that is leaving the tank. If you were part of the May 1st mock exam, we went over a question that was very similar to this one. So I'm first going to say my leaving rate equals my entering rate, because that's pretty much what the question says. Another interpretation of this is to find where W minus R equals 0. And that consideration is going to earn you the first point. My strategy here is going to be to use this time interval and to show at one of these times my W minus R is less than 0, and at the other time my W minus R is greater than 0. So if we're going to go from a number less than 0 to greater than 0 or vice versa, we must hit 0 along the way. And what that is IVT. So I'm going to go ahead and find W minus R of 0, and I get a 660. When I plug in 8 into those functions, I get a negative 618. And I can see, since I go from a positive value to a negative value, I must hit 0 in order to get there. And that is pretty much the IVT, but I have to lay out all the necessary steps of the IVT, which is to first recognize that we have a continuous function. What we're told about W and R is that they're differentiable, but I can conclude that they're continuous, so I'm going to use the IVT. You don't actually have to mention IVT, but if you know that's what you're using, you can do that. If you call it MVT at this stage, then you don't get this point. So be sure you're using the right theorem's name as you're doing this. The second thing I have to do is position my 0 in between the W of minus R of 8 and the W minus R of 0. I've actually already done that up here, so I wouldn't actually have to say it again, but I did. And then my last step is just to summarize my answer. Therefore, there is a time where W minus R equals 0, which proves that there is a time where W equals R. Point-wise, if you have this W minus R equals 0, if you considered that, you're going to earn a point, and everything else is going to be worth a second point.